matrices. So we've already done the matrices, you know a little bit about it. This is something you can use it for. The Gaussian elimination is a method used to transform a system of equations into a triangular form. So anyway, here is if we take a matrix, or this is an augmented matrix. If we have a matrix used to represent a system of linear equations. So if we have our linear equations like you see right here, and then we put it into matrix form, then what it is just the coefficients only in the order of a standard form, basically. So it would look like that. On an augmented matrix, any of the following actions, like switching two rows, multiplying a row by a constant, adding one row to another, is known as row operations. By using row operations to obtain triangulation of a matrix is called row echelon form. When the matrix is in reduced row echelon form, the solutions are obtained. So for instance, this would mean x is 6, y is -2, and z would be 3. Okay, because there was just ones here. The coefficient of the x, y, z would be 1, and the coefficients of the others would be 0, so they would not be there. So on example 1, right, the augmented matrix, this is probably the easiest part. This would be 5, 4, 4, -2, 7, and 16. I probably should not have written it in that order because it generally goes in the other direction. A lot of times you'll see like a line right there. Not always though, so you don't necessarily have to put that. If you notice, it's not in this one, but it was in the one at the top. So sometimes you do see it. I generally don't put it there. So on B, this would be 1, 3, -2, 9, 2, 0, -6, 2, 0, 2, -2, 8. So just make sure that you put zeros for anything that's missing, and make sure you put the signs there and all that fun stuff. So example 2 says, write the system of linear equations represented by the augmented matrix. Use variables x, y, and z. So if I were going to take this and write it back into the other form, then this would be x plus y minus z equal to 2, 3x minus 2y equal to 2, and 5x plus 3y minus z equal to 1. So that's what it would represent. On part B, x plus y plus z is equal to 6, x minus 2y is equal to 9, and no x right there, that's a 0. 3y plus 4z is equal to 6. So that represents the same exact thing. Now as far as applying row operations on a matrix, you can do lots of different things. Basically the same thing we did when we do like elimination and stuff when we're solving them. Just so you're not writing the x's and the y's. But on example 3, using the matrix below, find a row operation for the following. So A, having a 0 in row 1, column 2. So row 1, these are columns up and down, rows are this way. So row 1, column 2. So I want a 0 right there, is what they're asking us. So what can I do to get a 0 right there? Well, I know I can say row 2 minus 2 row 1. Of course, actually I wrote it opposite. I wrote it as -2 row 1 plus row 2 on my paper. But either way, if I multiply this one by -2 and then add them together, that's going to give me a 0 right there. So if I multiply this top row by -2, that gives us -2, -4, and then -10. The bottom one stays the same. So if I add that together, then that top row would then be 1, 0, and -3. Bottom row stay the same because we didn't actually do anything with that. Okay, we're just looking at one piece at a time. So it's just like elimination, basically. You're adding things to eliminate something. Okay, so on part B, having a 0 in row 2, column 1. So if I want a 0 here now, we're looking at that piece, then I could multiply this one by what, -3 to make these two, make that cancel out. So I'm going to say -3 times row 1 plus row 2. That's what I'm doing. So first row stays the same. Second row, first row doesn't stay the same. Good thing we got erasers, right? Okay, this would be first row times -3, -3, and negative. I'm looking at the wrong one. Dang it. Let's use this one, because actually they have us. This is the same one. So I'm going to use this one to get that instead of the original. I should have told you that, because remember, it's kind of like when we already worked on E1, it's still equivalent, we keep going. So this is actually, well, yeah, that'll still be the same because the one's the same. But what I'm doing is I'm taking part A and multiplying basically this whole row by -3. And then this one stays the same here because I'm going to add those two together. So that gives me that gives me 0 here, 4, and 16. The first row is the same as what was right there. You see how I'm just bringing it down. I'm sorry, I could probably do a little better than this. It's just a lot going on, y'all. I know it is for y'all too, right? Okay, part C, having a 1 in row 2, column 2. So at this point, because what we're trying to do is clean it up to get to that reduced as a row echelon form. So I've gotten the 1 here, I've got the 0 here, I've got the 0 here. Now I need a 1 here. How can I get a 1 here? I notice I can just divide that by 4, can I? I could just say 1/4 of row 2. So then this first row is already in the form I need it. Now the second one, if I divide everything by 4, would give me this. So this actually means that the x value is -3 and y is 4. That's what it ends up meaning. That's the whole point of using the matrices to do that. Now on the next page, oops, down the back. Next page at the very top, solving a system using matrices. So on this one, we're going to write the augmented matrix. So this is, let's see, it would be 1, 1, -2, 6, 0, 1, 3, -8, 0, 0, 1, -3. Remember, because I'm just putting the coefficients of each one of those down, basically. So now they're kind of telling us how to do this. It says, perform the indicated row operations, state the solution. So on the first one, they're telling us to get a new row 2, we're saying -3 times row 3 and adding it to row 2. And if you could do this all at one time, it really is helpful. It's easy to get lost in the details of it, though. So right now, I'm not only changing row 2. So what I'm going to do is I'm going to go ahead and put down the other rows, because I know row 1 and row 3 are staying the same, okay? But this middle row, I'm going to say -3 times this one, and then add it to that one. So -3 times 0, 0, plus 0 is 0. -3 times this is 0, 0, plus 1 is 1. Because remember, we want a 1 right there, so we don't want to change that. Okay, 1 times -3 is -3. -3 plus 3, that's 0, which was what we needed it to be, right? And -3 times -3, that's 9. 9 minus 8, or plus a -8, that would be 1. Okay, so we just did that. And we got this first piece looking like we need. So now we're going to have to work on this one and this one. So I know we're changing row 1, and obviously we are. So on row 1 here, they're saying to the new row 1 is taking row 1 minus row 2. So this one minus this one. So that gives me 1, 0, -2, and 5. because I'm just subtracting those two. So those are a little bit easier to do when you don't have to do multiply or several steps. It's easy to make mistakes on it though. So that's my new one there. And so now I'm taking this one. Let's say we're going to say the new row 1 is going to be 2 times row 3 plus row 1. So 2 times this plus that. So that would be 1. 2 times this plus that is 0. 2 times this plus that is 0. 2 times this, that's -6, plus 5 is -1. And then these two stay the same. It's a lot of thinking. Kind of got to pay attention. So what does this actually mean? This means that x is -1, y is 1, and z is -3. And I know what some of you are thinking. Why do I have to learn it this way? Why can't I just solve it the way I can? Essentially, I guess you could. You know, I'm wanting you to see it, be exposed to it. It depends on what you go into in the future. If you go into something that needs linear algebra, you're going to have a bunch of this stuff again. The good thing is a lot of this can be done on your calculator, which we will get to if you have access to a graphing calculator. If not, I guess we'll make some adjustments for that. But yes, you can essentially solve it the way you know how with the 3 like we did in 7-1. I kind of prefer that way personally, just because I'm so familiar with it that I don't see a need in learning a different way. But some people might prefer this, and that is absolutely fine. You do what works for you, and I'm okay with that. Okay, so, but we are going to go through this example. So first thing on example 5, we're going to put these in the right, or in a matrix. So 1, -1, 1, -4, 2, -3, 4, and -15, 5, 1, -2, and 12. Okay, so here's my original one. Now remember, our goal is to get it to be in reduced row echelon form. So I want like a 1 here, 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 and zeros in these places. Really doesn't matter what those are, because they'll just be whatever they are. So I'm thinking it might be easiest just to start on that first row to get zeros here. Okay, hopefully you can do a lot of that in your head. So the first row I'm not even going to change. I'm just going to bring it over. And then this one, for me to get a 0 right here, I'm going to have to say this minus 2 times this, right? So actually, you know what? Let me write it on the side. Let me see if I can squeeze this in. I'm going to say row 2 minus 2. Well, actually, I need to go the, I guess it doesn't matter here, but if I go this way, that's going to leave me a negative right here. What if I switch it around? What if I said 2 row 1 minus row 2? Oh, I don't know if that's going to make a difference. Probably wouldn't matter which way you subtracted it, because you're going to end up having to get down to the same things anyway. Just might be a little bit different. That would give us 0. So 2 times this is -2 minus a -3 would be +3, so that would give me a +1. Oh, good. That gives me what I need, because I need a 1 right there. And then 1 times 2 is 2. 2 minus 4 is -2. And then -4 times 2 is -8 minus a -15, so it's +15. So that would be 7, I believe. Okay, so then the next one we have, how am I going to get it? I'm going to have to say 5. Yeah, 5 times this one minus this one. So 5 row 1 minus row 3. That's what I'm going to do on that one. So this would give me 0. -5 minus 1 is -6. 5 minus -2, so that's +2, so it's 7. 5 times -4 is -20. Minus 12, this is minus 32. Wow, that's a big number. Okay, so now I got the zeros here. So next step, I need a 1 here and zeros here. Well, I can add these two rows together, right? Just to get that one, so yay, let's do that. So the first row, I'm going to say row 1 plus row 2. So that gives me 1, 0, negative 1, 3. Second one, I'm just going to leave and bring down. The third one, let's see, I need a 0 right here also. That one looks a little more complicated, huh? I'm going to use the middle row, this one. Okay, so I'm going to say 6 row 2 plus row 3. So that gives me 0. Because we don't want to pick anything that's going to change that because we already have the zeros. This would be 0. That's negative 12 plus 7, just negative 5. And then 6 times that is, wait, I'm messing me up. 6 times that, 42 minus 32. I have 10. Hopefully that's right. Okay, so now we've got the zeros here, the 1's here. Now I just got to row on this row. So I need this to have a 1 right here. Well, I see that these two are divisible by 5, so I can just say negative 1/5 of row 3 to get that piece. I'm going to do that first, and then I'll have something to work with, because it's easier when you have a 1 right there to work with. Okay, so now that I've got the 1 right there, now I'm going to use this to do these two. So I know I can add these two together, and it'll get rid of this one, and not change these, which is what I need. So I'm going to add row 1 plus row 3, which gives me 1, 0, 0, 1. The bottom one's already fixed, so that's what I need. And then, let's see, I can say times 2 on this one, right? 2 times this plus that one. So 2 times row 3 plus row 2. So it doesn't change that, doesn't change that, just comes 0. That would be negative 4 plus 7, so it's 3. So now that we finished, this means x is 1, y is 3, and z is negative 2. I find it's a lot. Like, I don't think it's any simpler than the way we did this in 7-1. I kind of prefer 7-1. That's just me, though, so you don't necessarily have to worry about that part. But you need to kind of understand it, have some background, because you never know what your future holds and what you may be asked to do. Okay, so let's look at the next little part. Okay, last little bit is solving systems with inverse matrices. If matrix A has an inverse matrix, then you can solve a system like that, which they show you there. Basically, you just do the inverse matrix, multiply by the inverse matrix on both sides. It's kind of like multiplying by the inverse on both sides to solve an equation on basic. It just has to do with the matrices. So on example 6, that's what this one is. Basically, you would have to find the inverse matrix first. Well, let me write it first. That's what we should do. We should write it in matrix form. This means 3, negative 1, negative 2, 1 times x and y would be equal to 4 and 5. Okay, so that's basically what this equation means. So the first thing I need to do is find the inverse matrix, which, remember, when we do that, it's 1 over the discriminant, which is these two minus these two times each other. So that's 1 over 1. Well, golly gee, that's just 1. Anyway, okay, and then for the matrix itself, you swap these two, change the sign, change sign. So that means I have xy would be equal to the inverse matrix, which is this, times the 4 over 5. And if you multiply that out, you get 9 and 23. So x is 9, y is 23. Now, if you don't really want to do it in that method and you want to use your normal things where you use your elimination, I'm totally fine with that. I kind of prefer it myself. All right, the last little part is example 7, and this is not as bad as it seems. It looks really weird, but basically it says network analysis is important in computer science. In a network, it is assumed that the total flow into a junction, basically each circle, is equal to the total flow out of the junction. Set up a system of linear equations representing the network below. Solve the system using the capabilities of a graphing utility. So you can pop that baby in your calculator if you like. And well, actually, I'm going to assume you guys don't have one with you. I can show you how to do it whenever we get back to school, or you can learn it on your own. You can Google that. It's really not a big deal. I'm not going to ask you to do that on the test using the graphing utility. But anyway, what this means is, you see how like going into 1 we have x sub 1 is going into circle 1 and 15, but x sub 2 is going out of 1. You got to look at the way the arrows go. So basically this means I'm going to put circle 1 just to show you. X sub 1 plus 15 would have to equal x sub 2, because the 2 going into the circle has to equal what's going out of the circle. Then for, say, the second one, right? Second one, x sub 2 is going in, and x sub 3 and 18 are going out. So x sub 2 would have to equal x sub 3 plus 18. That's how it would be set up. And then on the third one, 3, we've got x sub 1 going out, x sub 4 going out, and 18 going in. So for 3 we have 18 has to equal x sub 1 plus x sub 4. Okay, for the fourth one, x sub 4 is going in, x sub 5 is going out, so x sub 4 is equal to x sub 5. And then for the fifth one, let's see, we've got x sub 3 going in, x sub 5 going in, so x sub 3 plus x sub 5 has to equal what's going out, which is 15. Alright, so we have them all written down. Now to write this as a matrix, we want to make it all line up properly. So this would be x sub 1 minus x sub 2 equal to negative 15. This would be x sub 2 minus x sub 3 equal to 18. This would be x sub 1 plus x sub 4 equal to 18. This would be x sub 4 minus x sub 5 equals 0. This is exactly what it is. X sub 3 plus x sub 5 equal 15. Okay, so if I wrote this as a matrix, then lining everything up, it'd be 1, negative 1, 0, 0, 0, negative 15, because it's x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and then the number at the end over there. So this would be 0. I might better write smaller. I don't know if I can fit it all in here. Okay, 18, and then we've got 1, 0, 0, 1, 0, 18, 0, 0, 0, 1, negative 1, 0, and 0, 0, 1, 0, 1, and 15, like that. Okay, so that's what it would look like. Now, my notes on the side, if you wanted to solve this with a graphing utility and you want to just play around with it, you have to hit the second button and the one that has the matrix, I think it's like in blue or something like that. It would be right above that x negative 1 key. And you would tab in, well, first you'd have to enter the matrix into your calculator. Assign it a letter, enter it in, and then you have to go down to like the math part and go to that RREF, reduce row echelon form. And then you have to go back and tab it in to put in, like, say if you named it matrix A, and after you've typed it in, you would do that. So that's how it would go in there. Now, anytime you have like you'd have infinitely many solutions if you end up with a row of like all zeros in it like that. I think that may come up because I notice I have some notes on that. But again, we'll talk about that sometime later if and when we get to it.